So at this point, we can take the logarithm of both sides. What base should we use? We'll use e as the base to take the logarithm. This is called taking the logarithm of both sides. To reduce the power, take the logarithm of both sides to reduce the power. Okay, so in this case, we have ln of 3 over 2 on the left side. And on the right side, we have ln of 4 over 3 to the power of t. We can move the t directly to the front. Whenever there's an exponent, we can move it to the front. So that means we have ln of 3 over 2, which is equal to t times ln of 4 over 3. So that means the t that I want is equal to our ln of 3 over 2 divided by ln of 4 over 3. Okay, so now let's process this. That is equal to our ln of 3 minus ln of 2. In the denominator, it's ln of 4 minus ln of 3. Ln of 4 is 2 times ln of 2 minus ln of 3. So at this point, it's approximately equal to, in the numerator, 1.10 minus 0.69. In the denominator, it's 2 times 0.69 minus 1.10. So that means it's exactly 10 minus 9 is 1, and then 10 minus 6 is 4, so that's 0.41. In the denominator, it's 2 times 9 is 18, so that's 1.38 minus 1.10, which is exactly 0.41 divided by 0.28. So you just use 41 divided by 28, we get a 1, 28. What's left? 13, right? Okay, so 1 point something. Is 5 enough? 5 times 8 is 40. No, let's use 4. 4 times 8 is 32. This is 0. 4 times 8 is 32. 112. We have 18 left. For 18, we can definitely use 5. How about 6? 6 times 8 is 48. Yes, 6 works. 6 times 8 is 48. 2 times 6 is 12, 168. We have 12 left. It's 1.46 something. 1.46 something is approximately, note, accurate to 0.1. So that's 1.5. This means that from the initial 60%, it can reach 90% after 1.5 hours. Note how much more time is needed. 0.5 hours is enough. It's how much more time is needed. Pay close attention to this information. Okay, so next is the study of the problem of the range of values for the 0 point. Then you definitely need to quickly draw the graph of fx. Come on, let's draw it quickly. For the graph of the function less than or equal to 0, hey, one root is exactly 0 and another root is -2. See? Because its axis of symmetry is exactly -1. You can also calculate its roots on the left and right sides. And the opening is downwards. So that means when you draw the graph, it's as shown in the figure. You must draw the graph here. So at -1, it reaches its maximum value, which happens to be 1. And on the right side, for log base 2 of x, this logarithmic function with an absolute value, well, we just use the rule from class, reflect the bottom part up, and we're done. This point is 1. Okay, now you tell me that fx minus t equals 0 has 4 different solutions. Essentially, this just means that fx equals t has 4 different solutions. This is equivalent to y equals fx, and y equals t having 4 different intersection points. That's all. So, as shown in the figure, how many do we have? 2 intersection points. That doesn't meet the condition. Let's move it down. How many now? 4. If we go down to 0, we have -2, 0, and 1. 3 intersection points. That's not allowed. So this means the range of values for t is from 0 to 1, which is an open interval. Okay, now let's continue. We need to find the range of x1 plus x2 plus x3 plus x4. So let's label them. We can say this is x1, this is x2, this is x3, and this is x4. So based on symmetry, we have x1 plus x2 divided by 2, which must be equal to -1. This means that x1 plus x2 equals -2. We can just establish this relationship first. Okay, and for the absolute value of the logarithm of x to the base 2, there's a property that says x 3 times x4. Their product is a constant, which is exactly 1. So this means the expression you want me to find can be rewritten as what? As -2 plus our x3 plus x4. x3 is equal to 1 over x4 plus x4. So this means if I can just find the range of x4, the problem is solved. It's very simple. Okay, so in that case, the rightmost value that x4 can reach corresponds to when our this t is equal to 1. Okay, you want it to equal 1. Log base 2 of what equals 1? It's exactly 2, right? So this means my x4, as this line y equals t, moves between 0 and 1, your intersection point x4 must be to the right of 1. So it must be greater than 1 and less than what? Less than 2. So in that case, when I calculate the range of this expression, then based on x4 plus 1 over x4, it follows the shape of our hook function. So this means we draw the graph of the hook function. You just need to draw the graph of x plus 1 over x. The x here is our x4. So obviously it reaches its minimum value at 1, and at 2 it reaches its maximum value. Note that it can't be 1, so it's an open circle, and it can't be 2 either, also an open circle. So in that case, if we plug in 1, it reaches its minimum value. So that means it's 1 plus 1, which is 2. And if we plug in 2, we get the maximum value. 2 plus 1/2 is 5 over 2. So this means the entire expression, negative 2 plus x4 plus 1 over x4. The function value of f of 1 should be 2. The function value is 2. So that's negative 2 plus 2, which is greater than 0. Less than 5 over 2 plus negative 2, which happens to be 1/2. So this means that in the end, we can get the range of this expression is an open interval from 0 to 1/2. Since it's an open interval, it can neither be 0 nor what we call 1/2. This is the fill in the blank part. Overall, it's not too difficult and it's all acceptable. It says, given that sine of pi over 2 plus alpha is equal to negative 3/5 and alpha is an angle in the third quadrant, then we are asked to find the value of sine of alpha. So when we get this structure, what it's testing us on is based on this part here, a test of the reduction formulas. So this means that when you get this, you need to use the reduction formulas to process it. This means you have to have the reduction formulas memorized clearly. Okay, in that case, according to the problem, sine of pi over 2 plus alpha, then in this case, it is exactly equal to our cosine of alpha. The mnemonic for this is odd changes, even doesn't. The sign depends on the quadrant. Now, odd or even refers to the k in k pi over 2. In this case, k is 1, so sine changes to cosine, and cosine changes to sine. It becomes cosine of alpha here, sine changes to cosine changes to sine. Now for pi over 2 plus alpha, if we treat alpha as an acute angle, it's in the second quadrant. The sign in the second quadrant is positive, so it's cosine of alpha. So in that case, what does it equal? It equals our negative, what's called 3/5. Okay, cosine of alpha is equal to negative 3/5, which is completely consistent with it being in the third quadrant where both sine and cosine are negative. Okay, and then because of what? Also, because the square of sine of alpha plus the square of cosine of alpha is equal to 1. So this means that we can find the cosine, we can find the value of sine of alpha here. So this means we have sine of alpha, which is equal to plus or minus the square root of 1 minus the square of cosine of alpha. So if we substitute the value, it's exactly plus or minus 4/5. Because alpha is an angle in the third quadrant, it means that sin of alpha is less than 0. And from that, we get that the sin of alpha we need is equal to negative 4/5. And so we get our sin of alpha. Okay, for the second part, we need to find the value of this expression. So this means that when I get it, f of alpha is equal to, we process it based on the reduction formulas here. For tangent of pi minus alpha, it's also supplementary to alpha. When you remember the rule for supplementary angles, the sine values are equal and the cosine values are opposite numbers. So this means it's equal to negative tangent alpha, and then multiplied by sine pi minus alpha, which is actually exactly the sine alpha we need. Then multiply it by sine 3 pi over 2 minus alpha. Since 3 is an odd number, it means it will definitely become cosine alpha. Then at this point, 3 pi over 2 is exactly 270 degrees. 270 degrees minus an acute angle is in the third quadrant. In the third quadrant, the sine value is negative, so we add a negative sign. Okay, the denominator is cosine pi plus alpha. It remains unchanged, cosine alpha. Hey, pay attention. This position is 2k over 2, and 2 is an even number. It's called 2 pi over 2, and it's cosine alpha. Now, pi plus an acute angle is in the third quadrant. The cosine value in the third quadrant is negative, so we add a negative sign. In this case, negative, 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 3 negatives. So the final result is negative. Let's see if anything cancels out. Cosine alpha and this cosine alpha cancel out. So that means the remaining result is tangent alpha multiplied by our sine alpha. Since we know that tangent alpha can be written as sine alpha divided by cosine alpha, the numerator becomes sine squared alpha divided by the denominator cosine alpha. So the final result is sine squared alpha, which is negative 4/5 squared 16 over 25 divided by cosine alpha. Cosine alpha is given in the condition, which is negative 3/5. So the two negatives make a positive. One of the 5s cancels out. That means the denominator is 3 times 5, which is 15. So we have 16 over 15, and that means we've found the answer, the value of f alpha. So in the process, hey, we used what we call the reduction formula. Remember the reduction formula clearly, and you can simplify the angle accordingly. Okay, next, let's look at the next one, which is a problem about the relationship between this set and sufficient and necessary conditions. Okay, so now the first set, set A, tells us that 3 to the power of x minus 4 is greater than or equal to 1/3 and less than or equal to 9. Set B is also given. We need to find A union B. So because the condition is given, 3 to the power of x minus 4 is greater than or equal to 1/3 and less than or equal to 9. So that means x minus 4 must be greater than or equal to 1/3 is 3 to the power of negative 1 and 9 is 3 to the power of 2. So that means x is greater than or equal to 4 minus 1, which is 3, and less than or equal to 4 plus 2, which is 6. That means set A is x, where x is greater than or equal to 3 and less than or equal to 6. Okay, now let's look at set B. For set B, the logarithm of 1 plus 2x with base 3 must be greater than 2. 2 can be written as the logarithm of 9 with base 3. So that means 1 plus 2x must be greater than 9. 2x must be greater than 9 minus 1, which is 8. So x must be greater than 4. So this means that for set B, it's x, and x must be greater than 4. In that case, we know both set A and set B, so we can find the union of A and B. 1 is greater than or equal to 3 and less than or equal to 6. The other is greater than 4. So this means their union is just x is greater than or equal to 3. Okay, now let's look at the second part. So for set C, it's this is x squared minus 2mx plus m squared minus 1, which must be less than or equal to 0. Then if x is in C, it is a sufficient but not necessary condition for x to be in B. The former can imply the latter, but the latter cannot imply the former. So this means the smaller range can imply the larger range. In that case, C is a proper subset of B. So this means when we get this, I need to factorize x squared minus 2mx plus m squared minus 1 is less than or equal to 0. We've said that when you get these two terms with parameters, it's highly likely that they can be factorized. M squared minus 1 becomes m plus 1, m minus 1, and negative 2m. So this means it's exactly x minus. This is called m plus 1. Times x minus m minus 1, which must be less than or equal to 0. Hey, if you calculate it yourself, you'll find there's no problem. In that case, you'll find that the parabola opens upwards. One root is m minus 1, and the other root is m plus 1. m minus 1 is definitely smaller than m plus 1. So this means we take the middle part, so x is greater than or equal to m minus 1, and less than or equal to what? M plus 1. Now because x is in C, this is set C. The range of set C is enough, you'd better write it down. So this means that for set C, it's x, where x is greater than or equal to m minus 1 and less than or equal to m plus 1. Because x being in C is a sufficient but not necessary condition for x to be in B. Okay? Because it's a sufficient but not necessary condition, it means the relationship we get here is small implies large, but large cannot imply small. So this means the former is what we call a proper subset of the latter. You must get this relationship. Okay, so this means that C is a proper subset of B. In other words, C is contained within B. Now, since we already found set B in the first part, this means, take a look, I have to fit inside you. So the number m minus 1 must be greater than what? Set B is greater than 4, right? I'm being fitted inside. You can draw a diagram yourself. This position is 4. I have to fit inside you. So this means m minus 1 is greater than 4. Can it be equal to our 4? No, because if it equals 4, set C can include 4, but our set B cannot, so that won't work. Solving it, we get that m is greater than 5. Let's write that down. So this means that the range of values for m is the open interval from 5 to positive infinity. Note that 5 is not included. Okay, next up is a mathematical problem, specifically about what we call a quadratic function with a moving axis and a fixed interval. Okay, so now let's take a look. Given that this quadratic function is x squared minus 2x minus 3. Now, if the solution set of this inequality is from -1 to 3, we are asked to find the value of the real number a. So according to the problem statement, we know that the solutions to this inequality, well, the endpoints are exactly the roots of the corresponding equation. So this means for the first part, from the problem statement, what is it? It's that x is equal to -1 and 3 are the values that are the roots of x squared minus 2x minus 3 equals 0. Now, since they are the roots of this equation, it means you can use either the sum of the roots or the product of the roots. Both will work. So -1 times 3 is exactly equal to -3 over a. And that means if we solve for a, it's exactly equal to 1. You can use either method, either one works. All right, okay, you can also verify it yourself. When a equals 1, there's no problem. And then for the second part, it says when x is in the interval from t to t plus 1, we need to find its minimum value. So now we already know my f of x is x squared minus 2x minus 3. So the opening of this parabola is upwards, and this position here is 1, this is 1. Okay, right now, I don't know if the interval from t to t plus 1 is to the left of, in the middle of, or to the right of the axis of symmetry. So this means we need to discuss it in cases. If, in the first case, your t plus 1 is less than or equal to 1, or equal, which means t is less than or equal to 0. That means the given interval is this segment here. So that means, obviously, since your interval is on the left side of the axis of symmetry, then f of x is monotonically decreasing on the interval from t to t plus 1. And that means at this time, our g of t is exactly equal to f of t plus 1. So substituting t plus 1, we get exactly t plus 1 squared. Minus 2 times plus 1, minus 3. So in this case, after expanding it, we have to square it. Then 2 times t times 1 is 2t minus the 2t at the back, so it's gone. In the front, there's a constant 1. 1 minus 2, and then minus 3. So that's -1 minus 3, which is -4. Okay, and then next is the second case. The second case requires that my axis of symmetry falls within this interval in between. So that means for the second case, 1 must be greater than t, and at the same time, less than t plus 1. So in this case, that is, t must be greater than 0 and less than 1. So it's clear that the corresponding function f of x is monotonically decreasing on the interval from t to 1. And then from 1 to t plus 1, it's monotonically increasing. That means my g of t is obtained at 1, which is f of 1. So at this point, substituting 1 into f, we get 1 squared minus 2 times 1 minus 3. 1 minus 2 is -1. -1 minus 3 is exactly -4. Okay, the third case is when this interval is on the right side, this position is t. That means when t is greater than or equal to 1, the corresponding function f of x is monotonically increasing on our interval from t to t plus 1. So that means g of t is obtained exactly at t, which is f of t, and f of t is exactly t squared minus 2t minus 3. Finally, you should write down the summary yourself. To summarize, this g of t is equal to t squared minus 4. When t is less than or equal to 0. then it's equal to negative 4 when t is greater than 0 and less than 1. It's equal to t squared minus 2t minus 3 when t is greater than or equal to 1. That means in this case, there are 3 segments. 3 segments. Okay, so write it out as a summary to make sure you get full marks for this. Okay, then let's look at question 18. Well, question 18 has what we call a composite logarithmic function, and we have a composite of what we call an exponential function. So it's a double composite function to test us. Okay, first, we are given an f of x, which is a composite of a logarithm and a quadratic log base 2 of x squared minus 2ax plus 3. First, when a is equal to 1, we need to find the minimum value of f of x. This one is a bit of a giveaway. So that means for the first part, when the value of a is equal to 1, the function f of x is equal to the logarithm with base 2 of x squared. And then we subtract something from this result. Here, log base 2 means we are taking the logarithm of x squared using 2 as the base. Minus 2x, and then add a 3. Okay, so for the argument x squared minus 2x plus 3, let's rearrange it. It can be completed into the square of x minus 1. This way we have x squared minus 2x plus 1. You need to add 3, so we add another 2. So obviously the square of x minus 1 is greater than or equal to 0. If we add 2, it becomes greater than or equal to 2. Since it's greater than or equal to 2, it means that my f of x is greater than or equal to log base 2 of 2. And your log base 2 of 2 is 1. That means the minimum value of f of x is equal to 1. And so we can get the minimum value here, the minimum value. Okay, you can also express it using monotonicity. That's no problem at all. It works either way. Next, it says if f of x is monotonically increasing on the interval from 2 to positive infinity, then we need to find the range of values for a. What is it? Okay, so at this point, this is a test of the monotonicity of this composite function. Now at this point, we can let the variable u be equal to x squared minus 2 times a times x plus 3. Then the variable y, which is actually our function f of x, can be written as the logarithm with base 2 of u. This means that, in other words, y equals log base 2 of u, where u is defined as x squared minus 2ax plus 3. Okay, when we write this y as log base 2 of u, we know that log base 2 of u is definitely monotonically increasing. So it comes down to this quadratic function here. Now for this quadratic function, for the function u, where u equals x squared minus 2ax plus 3, it is quite clear and evident that on the interval starting from its axis of symmetry, which is located at the value a, and extending all the way to positive infinity, the function is monotonically increasing throughout this entire range. You can, if you wish, write this out in words yourself for further clarity. So that means, and pay attention here, your axis of symmetry must be to the left of our interval, right? If you draw a diagram, it becomes clear. Look, it's like this, right? Your axis of symmetry is A, and we need it to be monotonically increasing from 2 to positive infinity. So that means our A must be less than or equal to 2. At the same time, you need to satisfy that it's monotonically increasing from 2 to positive infinity. So the function value we get when we plug in 2, which is the value of u. The value of u must be in the position of the argument, so it must be greater than 0. So that means we have 2 squared minus 2a times 2, and then plus 3 must be greater than 0. Okay, let's solve it. 2 squared is 4. 4 plus 3 is 7. 7 must be greater than 4a. So from that we can solve 4a, which must be less than 7 over 4. So that means the solution is a must be less than or equal to 2. And at the same time, a must be less than our 7 over 4. It must be less than or equal to 2, and also less than 7 over 4. So that means a must be less than 7 over 4. It must be less than or equal to 2, and also less than 7 over 4. So to answer, its range is the open interval from negative infinity to 7 over 4. Okay, now we're told there's a function called g(ex). Hey, we're very familiar with this structure. 4 to the power of x can be written as 2 to the power of x squared. It's just a composite of an exponential function and a quadratic function. If the inequality gx is greater than or equal to our f0 holds true, we need to find the range of x. So this means for our third sub-question, when I get to it, gx is greater than or equal to our f0, it becomes equivalent to 4 to the power of x minus 2 to the power of x plus 1 minus 3 plus log base 2 of 3 is greater than or equal to f0. Now for f0, it doesn't matter what a is. Hey, it happens to be log base 2 of 3. Let's see, it is indeed log base 2 of 3, so log base 2 of 3 and log base 2 of 3 cancel out. So this means 4 to the power of x can be written as 2 to the power of x squared, then minus 2 to the power of x plus 1 is 2 times 2 to the power of x, then minus 3. And what does that have to be? Greater than or equal to 0. All right, if you treat 2 to the power of x as a single entity, it's just what we call a quadratic inequality in terms of 2 to the power of x. So this means we can factorize it. 2 to the power of x minus 3 times 2 to the power of x plus 1 must be greater than or equal to 0. And we know that 2 to the power of x is definitely positive. So what does that mean? It must be greater than 0. Yes, it must be greater than 0. Okay, so in that case, what do we need to ensure? We just need to ensure that 2 to the power of x minus 3 is what? Greater than or equal to 0. That's all. That means 2 to the power of x is greater than or equal to 3. And x just needs to be greater than or equal to log base 2 of 3. So let's state the answer. So at this point, the range of x. So what is the range of x? From log base 2 of 3 to positive infinity, closed on the left and open on the right. And that's it. Yes, write the range in this interval format and the problem is solved. Okay, then number 19 is actually a little bit difficult. It's based on what we call the problem of function zeros, which is an important concept. As I've told everyone, when dealing with this part, students, at this point, you must have the idea of separating the parameters. Yes, you must have it. Okay, there is a function, a quadratic function, x squared minus 2, x plus 1 plus b, where a and b are both greater than or equal to 0. On the interval from 1 to 2, it has a maximum value of 1 and a minimum value of 0. Now let fx be equal to gx over x. Now we need to find the values of the real numbers a and b. Okay, if we say a equals 0, then you have a constant function. There wouldn't be any talk of maximum or minimum values. So this means, as we know from the problem, this value here definitely isn't 0. Let's write it down, because it only says that a and b are greater than or equal to 0. So this means that when a equals 0, your g of x is equal to 1 plus b. It has no extreme values. So this means a is not 0. That is, must be what? It must be greater than 0. So since a is greater than 0, that means for this quadratic function g of x, the corresponding quadratic term's coefficient is greater than 0. And that means it's a quadratic function that opens upwards. And its axis of symmetry happens to be x equals negative b over 2a, which is exactly equal to 1. So this means that our g of x is where? On the interval from 1 to positive infinity, it is monotonically increasing. Therefore, this g of x on the interval from 1 to 2 is also monotonically increasing. And that means the minimum value of g of x in this case is obtained at g of 1. Let's plug in our 1. Times 1 squared is a minus 2a plus 1 plus b, and that equals 0. Then the maximum value of g of x at this point will definitely be my g of 2. So if we plug in g of 2, that's a times 2 squared